We'll now take a look at the next part of the definition of an algorithm that talks about computable operations. So an operation is a step in an algorithm that performs some type of task, some type of action. So algorithms are composed of these things that we call operations. But what do these operations look like? What types of building blocks can be used for constructing such an algorithm? So the answer to these questions is that the operations in our algorithm have to meet two different criteria. The first one is that these operations have to be unambiguous. And the second one is that they must be effectively computable. To illustrate this, let's take a look at a possible algorithm for making a cherry pie. So the first step would be that we would make the crust. The next step would be to make the cherry filling. The third step would be that we would pour the filling into the crust. And then finally, we'll bake the pie at 350 degrees Fahrenheit for 45 minutes. So there we go. There's our algorithm. So now if we follow the steps, we should be able to make a cherry pie, right? Well, for professional bakers, this algorithm would be fine. They would know how to carry out each of these operations. They would know how to make the crust. They would know how to make the filling. That wouldn't be an issue. Now, for the rest of us who probably don't know as much about baking, I certainly don't know much about baking, we would have no idea what to do. We would have no idea how to make the crust or to make the cherry filling. Maybe we just hope there's a can that says cherry filling and that's all we need to make the cherry filling. But we have no idea how to do this. So that means more details are needed in these steps. So we need more detailed instructions in order to make our cherry pie. So let's see if we can improve the first step, the making the crust part, and adding some more specificity to it, adding more details. So let's say the first step would be that we would take 1 1/3 cups of flour. We'll then sift the flour. We'll mix the sifted flour with 1/2 cup butter and 1/4 cup water. And then we'll roll the flour into 2 9-inch pie crusts. So with this information, even inexperienced cooks should have an idea of how to create the crust. I mean, now there may be still some people who don't fully understand every single line, but for those people, we may have to add some more details with each step and describe the ambiguous steps. But the whole point is we take our steps, and if they're ambiguous, we add more details to them so they're no longer ambiguous. The whole point here is that we take ambiguous operations and we turn them into unambiguous operations, which we define as something that can be understood and carried out directly by the computer without needing to add any more breaking down any more details. We don't need to simplify the instructions anymore. We don't need to provide further explanation. We give a step to the computer and it can handle that step without any other information. So that's what we mean by an unambiguous operation. So when this happens, we say that the operation is primitive. So an unambiguous operation is a primitive operation. So that means our algorithm needs to be composed entirely of primitive operations. Now, it's not enough for an operation to be understandable. It must also be doable by the computer. So I mean, like, for example, if an algorithm tells the person to flap its arms very quickly to fly, well, we may understand what we're supposed to do. We may understand the operations, but it's still impossible to complete. I don't care who you are. You're not going to, if you flap your wings a bunch, or technically you don't have wings, you have arms. If you flap your arms, you're not going anywhere. So we can't do that. So to say that an operation is doable means that there must exist some type of computational process that allows the computer to actually complete that operation, complete that task successfully. So these types of operations are called effectively computable. So the whole point here is we're saying it's not enough just to understand a step, but we have to have a step that we can actually do. It has to be effectively computable as well. Let's take a look at an example algorithm. So let's say we want to print the 100th prime number, and here's the algorithm I'm going to use to do that. So the first step is to get a list, which we'll call L, of all the prime numbers. So L1, L2, L3, we just get all the prime numbers. And then we'll sort the list in ascending order. So we'll take our list L, we'll sort it in ascending order, and then we print the 100th element in that list. So that should be L100. And then we're going to stop. My claim is that this algorithm isn't going to work. So take a second to see if you can figure out what the issue is with this algorithm and why we can't use it to get the 100th prime number. Okay, so the problem here is we can't complete step 1. There's an infinite number of primes. I mean, so if there's an infinite number, then there's no way we can get all of them. So that means that step 1 is not effectively computable. I understand the step. The computer will probably understand that we need to get all the primes, but it's just impossible to get all of them because there is an infinite number of primes. We'll now take a look at the next part of the definition of an algorithm, where we're producing a result. So if we want to know if an algorithm is correct, well, we need to get some kind of output. There has to be some type of result generated that we can see. I mean, if there's no result printed, or if there's no output, how do we know whether our algorithm actually worked or not? So like, for example, if we have an algorithm that gets the sum of two numbers, well, it should produce the sum as the result. And we can check that and see, is that actually the sum of our two numbers? And if so, then our algorithm is good. If it didn't work, then something went wrong with our algorithm. But there has to be some type of result that's produced so we can check to see that our algorithm is in fact correct. Now, it's worth noting that the result could be something other than some type of output message. For example, it could be a set of lights. It could be some set of approximations. It could be error messages. So, I mean, there are other types of ways of producing a result than just some type of answer. But the whole point here is that our algorithm needs to produce some type of result. We'll now look at the last part of the definition of an algorithm that says that our algorithm halts in a finite amount of time. The point here is that an algorithm must stop at some point, because if it doesn't stop, then that means we have some set of steps that just keeps running forever. And we call this set of instructions an infinite loop. You do not want an infinite loop in your algorithm, because if you translate that into code, that means that your computer is going to keep running that set of instructions forever and ever and ever and ever, and it just never stops. That's usually a problem. So, like, for example, our shampoo algorithm was an example where we had an infinite loop where it would just say repeat, and it never gave us an indication of when to stop. So we can fix that if we wanted to. So we could say repeat steps 2 to 3 twice, and then we can add another step to stop. We could also add additional steps to lather and rinse. That we can specify exactly how many times we repeat and when do we actually stop. So I mean, there's a couple ways we can go about it. In fact, there's usually more than one correct way to write a correct solution. Now, some may be faster than others, but to solve a particular problem, there's usually more than one solution. So now we'll end the lecture by just answering the question, why is it important to have algorithms? What's the importance of algorithm problem solving? And I think I've mentioned a little bit before, but it's nice to just kind of reiterate the whole purpose of designing the algorithm. Once we have a correct algorithm where all the instructions are clear, they're unambiguous, they're efficient, they'll actually stop. Once we have all that set up, then we can turn it into a program that we can have run on the computer. And then our device would just simply follow the instructions and then just complete the task. It doesn't need to worry about the creative process or how we came up with those steps. It just needs to see the steps and it'll say, okay, I'll do this step and I'll do this step and I'll do this step, and it just performs all the steps. So we have a working program that allows us to automate the repetitive tasks. So instead of having to just do these tasks ourselves and just try to remind ourselves how to go about it, we just write a program that does all the work for us, so that way we don't have to worry about the repetitive mental tasks that's part of solving this problem. So turning it into a program is very, very useful for us.